This video is going to cover how to create an axial force diagram for mechanics of solids. This is a very simple process to create an axial force diagram, and we're going to talk about it and then we're going to do an example. But step number one is usually to find reaction forces, but technically it's not always required. We can write it down. Reaction forces are good to find. Step number two, we want to make a cut. And we're going to specifically make a cut between every time the load changes. So when you put a new load onto the member, then the load that's going on inside of it is changed. So every time we see a change in load, we're going to make a new cut. Step number three is we're going to draw free body diagrams for our cuts. Yes, just like before when we did an equilibrium of the deformable body, we made a cut at a certain spot. We're going to effectively do the same thing every single cut. Step number four for us is always to assume a positive direction. We always assume, for axial, we're talking the normal force. So we assume normal force in the positive direction. And remember that positive does mean tension. Tension is very specifically away from the face versus the negative one. Just as a recap, the negative direction is a compression, and that's going towards the face. So just as an aside here, remember that positive is always away from the face, and that's in tension. The negative direction is compression, that's towards the face. So on our free body diagram, we're always going to assume a normal force in the positive direction. And then obviously step number five, solve for the normal force. And then step number six is to repeat for each change in load, or for each cut as we called it just a second ago, right? So what we're going to do is we're going to calculate reaction forces. Maybe you want to put a little star next to this dude, because technically it's not required. There's very many instances where it is a very good thing to start by calculating the reaction forces, but technically at the end of the day, it's not required. Then we're going to make a cut, we're going to draw a free body diagram, always assuming the normal force in the positive direction, solve for said normal force, and repeat again, because every single one of these cuts right here, it's for every time the load changes, not necessarily direction, but every time there's a change in the amount of load that we have on our members. So every time there's new load, new force, we got to make a new cut. Easiest to see in an example. So for this example, it's a little bit big. Specifically, when I taught this course, I did a horizontal example, and so I'm going to do a vertical example. It does not matter whether it's horizontal or vertical, just rotate your page 90 degrees and bam, it's the same thing. So for this one, we're going to try and fill out our axial force diagram. As you can see over here, this is the goal, is to fill out this guy over here. That's what we want to do. And to do that, we have to solve this problem that you see on the side. Now you might think, ooh, what a hard problem. It's got weird shapes and stuff. And I'm here to tell you that it doesn't matter. Yes, it doesn't matter. So we have this goofy shaped thing. And again, all we're caring about is the normal force. That's axial. In this case, as just a little aside, that's the sum of the forces in the y direction. We're not calculating any moments. We're not calculating any x forces. We are simply looking at the forces in the y direction because that is the axis of the member. So in this case, it'd be like a column, and the axial force is down the axis of the column. So yes, if you were looking at a horizontal beam, then you'd be looking at forces in the x direction, but we are specifically looking down the axis of the member. So all we want is normal forces. So what we're going to do is, like I said, every single time that we have a change in load, we're going to make a cut. So step number one, let us draw out how many cuts we need to do. So there is a 4 Newton load going up here. There's a 7 Newton load going down there. You notice that I have labeled them A, B, C, and D here. So for these faces, that's where our loads are acting. So between face A and B, there is a change in load, right? Because 4 newtons was going up, then 7 newtons go down. So somewhere in here we need to make a cut. So I'm going to draw a line right there. That's my cut. Then as we go from B to C, you can see that B, there's 7 newtons going down. At C, there's 2 things of 6 going up. So we need to make another cut. So bam, we'll make another cut. From C to D, there were 2 things of 6 going up at C. There's 3 going down at D. So there's a cut. And then you might think, ooh, that's the end of it. However, remember step 1, technically, step 1 over here was to calculate our reaction forces. So we're going to have, let's call this EY. Right, there's technically a reaction. So because there's a reaction, at D, there's 3 newtons going down. At E, there's a different set of reactions. So that also needs a cut. So yes, the number of cuts that we're going to have for this is 1, 2, 3, and 4. So because of that, let's go ahead and calculate EY, just to start it off. No cuts yet, no cuts. We're just going to start off by, oh, that was ugly. We're going to start off by summing the forces in the y direction, setting it equal to 0. I've said it a lot, but I'll say it again. When you choose for your equations of equilibrium, you choose a positive direction. That's just to tell you which numbers get a positive sign next to them and which ones get a negative for this. That's all that they do. It's nothing else, nothing fancy like that. So I'm going to choose positive to be up, and we're going to go from there. So we start off, we've got a, maybe we should draw it with colors just to make sure everybody's on the same page here. We've got 4 newtons going up, then there's a 7 going down, so that's minus 7. Then we have 2 things of 6 both going up, so we have plus 2, 6 Newton forces going up. We have a 3 Newton force going down, so we'll minus 3 newtons there. And then technically how I drew it, EY is also going down, so we'll minus EY. Plug it in, we're going to get EY, and EY is equal to 6 newtons. Now, fun fact, I drew it down, and this became a positive number. What this means is that the direction that I drew the arrow, this positive number, we shouldn't highlight in blue, this positive number that you see here, this positive sign, means that the direction that it is currently drawn in is correct. So it does actually mean that this is 6 newtons going down. It has nothing to do with the direction that you assume positive for the equation. It has everything to do with the direction that you currently drew the arrow. That's all. That's all. So it is positive 6 newtons, which does mean that this is 6 newtons going down. So we can come over here and just put 6 newtons on our beautiful diagram. Okay, so step 1, reaction forces. Did it. Step 2, we're making a cut. So we're going to analyze one cut at a time. Each time you make a cut, remember that this is an imaginary cut. They do not exist. They do not roll over into the next thing. We're just going to make cut number 1. Then we're going to do all the stuff for it. We're going to pretend it didn't happen. Then we're going to go to cut number 2. Going to do all the stuff for it. Pretend it didn't happen. Move on to cut number 3. That's all we're going to do. So we're going to start off with, let's go over to the side here so we can see it. Cut number 1. What does cut number 1 look like? Well, anytime you make a cut, you have a choice. You can use one side or the other of this. And to be honest, I'm thinking that the downside of the cut, if you were to just cut here at spot number 1, I can either take the up, quote, half or the down half. And I really don't think the down half is a good half, to be honest. I think the up, quote unquote, half is better. So let's draw a free body diagram of up from cut number 1. Pardon my really bad drawings here. So there you go, looks like that. We got a 4 Newton force coming up. That's it. Between A and B, if you just, I know we cut the 7 right in half there, but if you just, in between A and B, that's all that's going on. Now remember, it's not really a full free body diagram until you come back through and you put on the normal force, right? The internal forces, that's all that solids is about. So let's put on the internal forces, remembering that step number 4, technically, step number 4 is we're always going to assume a positive normal force. Tension is away from the face. So if the face of my cut is right here, I need to go away from it. So that's away from it. This is going to be my normal force. Kind of sucks a little bit that I put newtons here, but this is just N, so maybe we don't like newtons. But anyway, so the normal force here is in green, and so hopefully make that a little bit easier for y'all. So quite simple problem, really. You look at that problem as it itself, it just cut 1, and all you got to do is sum some forces in the y direction and set it equal to 0. Again, picking a direction to be positive here is only for the sake of determining who's a positive number when he goes in and who's a negative number. So in this case, we have 4 newtons. Should make sure that's color-coded correctly. We have 4 newtons going up, and we have N going down, so N's negative. So at the end of the day here, N is equal to a positive 4 newtons. So what does that mean? That means, again, just to restate it, the positive here means that the direction that we drew this is correct. Now again, going back up here, the whole reason that we assumed that the normal force is always in the positive direction is so that when you get a positive here, it directly translates to over here. Now it's positive and positive because you always assumed it to be positive, so bam, so that it's lovely. It truly is lovely. It might seem pretty stupid at first to really make a big deal out about how it always needs to go in the positive direction, but if you do it that way, then it makes figuring out whether that normal force is actually positive or negative really easy. So again, the plus here means that yes, this thing was actually going in the correct direction, and that direction is again 4 newtons in tension. So tension side is the positive side, so the tension side is positive, the compression is negative. Usually instead of doing a plus and a minus over here on our axes, usually we'll put a T and a C, because again, tension is positive, compression is negative. Either one, kind of the same thing. So again, from A to B, nothing's going on no matter where you take it along in that y direction. From A to B, we have 4 newtons. So what we're going to do is we're just going to come over here, draw our line. That is 4 newtons, and we're just going to shade that in. Yep, there you go. You don't need to write the N because, again, we already wrote the N. He's right there. That's why we labeled it. So that's just the magnitude. The magnitude is 4, and it's on the positive side. Bam, done. That's all we're going to do. And now we are on the step of repeat for each cut. Yes, that's all we have to do, so repeat for every cut. So that was cut 1. Let's move on to cut 2. In the interest of keeping this all here, I'm going to pick up this guy and yeet him off into a corner. All right, now let's do cut 2. So for cut 2, I know you're probably thinking, oh, what a shape, we got triangles. Again, all we are actually doing is summing forces in the y direction, right? That's all we're doing is summing forces in the y direction. There's no moments. We're not taking no moments on this. We're just looking at vertical forces. That's all we're doing. So the shape is really irrelevant. So again, cut number 2, what's he going to look like? He is his column piece. This is a terribly drawn triangular thing. Maybe it goes down just a little bit, and then there's the cut. Yeah, so it's a very terrible drawn thing, but it is what it is. We got 4 newtons again going up. We're pretending that the cut 1 never happened. Never happened. Then we got 7 newtons going down over here. Then we have the cut. Again, the cut surface is right here. Always have normal away from the cut face, which is tension, so that's going to be going down here. There we go. That's all that's going on at cut 2. So let's do the same thing again. Let us sum some forces in the y direction. Set it equal to 0. Again, for this equation, I'm going to assume up is positive. Got to state it. Got to pick one direction to be positive. So what do we got? We have 4 newtons going up. We got 7 going down. And n's also going down, so he's also negative. So you do the math, and what do you get? You get that n is equal to 3 newtons, but we get him to be minus 3. Minus 3. So again, what does the minus mean? The minus means that the direction that you drew is wrong, which means he's supposed to be like that, going up. Again, which direction is that? That is obviously in compression, and compression is negative, so we're right back to square one of, because we drew it in the positive direction, the fact that it says -3 is in fact the answer. So we're going to come over here, and now it's a -3, so there we go, straight line, a 3, and we're going to shade it in. Yes, take no sizes here at value. Okay, this is why we put numbers next to those bars, because we are not drawing anything to scale. Yes, not at all. So the shape is honest to God irrelevant when you're summing forces in the y direction, right? So it doesn't matter that there's a triangle, it doesn't matter that there's a fat rectangle in here or anything. It could be different shapes, honestly. You could have a pentagon in there. It doesn't really matter whatsoever for axial force only. Okay, so cool, that was cut 2. So now we're going to pretend that didn't exist. So we're just going to yeet him off to the side as well. And then we're going to come back over here and do cut 3. So cut 3, maybe at this point you're getting a little bit tired of doing everything from the top down. Maybe you want to go bottom up. Maybe not. We're not there at that point yet. So sure, let's keep drawing this stupid shape. So we go down, then we have this triangle piece. Gosh, and then it goes down a little bit more, and then we have this fat piece, this rectangular piece, and we're going to cut right in the middle of that. Beautiful. Alrighty, so we got up here at the top, we got 4 newtons going up, we got 7 going down, we got 2 things of 6, we got 6 newtons on each side going up. Again, the cut is at the bottom here. That's the cut. And normal always goes away from the cut. So in this case, it's going down. And yeah, there it is. There's our free body diagram. So away we go. We're going to, again, we're going to sum some forces in the y direction. Set it equal to 0. Again, for this equation, I'm assuming up is positive. So let's see what we got. We got 4 newtons going up. Then we got 7 going down, so that's -7. Then we got 2 things of 6 going up, so plus 2 things of 6 newtons going up. Then we have n going down, so n is negative. So now when you solve that, what do you get? You get that n is equal to +9 newtons. +9 newtons. So what does that mean? Well, that just means that, again, the direction you assumed was correct, which was positive, so therefore this is a +9. So we come out over here, that's 9. Ta-da. If for some reason I can't do math, which is highly possible actually, just check my numbers again. The process is correct, even if I myself cannot quite do math at this time. So there we go, that's cut number 3. Sweet, moving on. We're going to yeet him off to the side like everybody else, so goodbye. And let's do cut number 4. And this is where we start going, why? Why do I really want to draw the same thing all over again, and this time get just a little past D and put in the 3 newtons going down? Why am I trying to make things harder for myself? If you just looked at this problem and you saw only make a cut here, would you pick the top side or the bottom side? Being honest with yourself, which one would you pick? You would pick the bottom. So you know what? Let's do that. Why not? So technically, when I told you that the reaction forces were optional, this is why. Up to this point, you did not use that reaction force we solved for, right? And technically, you could take the top half in air quotes there, you could take the top side of that free body diagram and you would still not needed to solve for that reaction force. You might think, I'm really tired of drawing that dang shape. Yep, fair. You might think that's a bit excessive to include all of those numbers, and you would be absolutely right. But technically, because we found the reaction force go us, that's what cut 4 looks like. We have this magical 6 newtons going down here. That faces the cut, and we again, normal always goes away from the face, so in this case, now it's going up. Bam, Dan. There you go. Much easier free body diagram, isn't it? And perhaps maybe for cut 3, you were sitting here going, I wish I took that side. You only have a 6 newtons going down, and then you have a 3 newton going down. Man, that would be so much easier, but technically, it don't matter. At the end of the day, you're going to get the same answer. So let's solve for this one, right? So now we're going to sum the forces in the y direction, set it equal to 0. I'll say up is positive for this equation. So n's going up, 6 newtons are going down, so 6 newton is negative. At the end of the day, what did we get? We got that n is equal to a positive 6 newtons. Again, positive meaning the arrow direction that we drew, which was up, was correct. And because we, of course, drew it in the positive normal direction, then, of course, now that actually translates to positive 6. So over here, we just draw a line, put a 6, bam. There's the diagram. Don't believe me that you could do it from either side? Let's check it out. Let's check it out. Let's do cut 3 again. Let's move this guy. Let's go eat him off into the corner. And let's go do cut 3. But let's do cut 3. Let's do cut 3 from the bottom. Let's do cut 3 from the bottom because I'm sure you really don't want to see me draw that entire lovely shape again one more time. So let's do cut 3. Let's see if it's the same. So cut 3, what does it look like? We got big fat rectangle. Then he kind of dead ends into the floor, right? We've got that, yep, we'll do this one first. We've got 6 newtons going down. We've got 3 newtons going down. That's the applied load there at face D. And again, that was the cut up at the top. So normal goes away from that, so normal goes up. You want to sum some forces in the y direction, set it equal to 0. We're still going to take up as positive for the equation. So that's going to start off with n is going up. Then we have minus 3 newtons. Then we have the reaction force of minus 6 newtons. So what do we get? We got n is equal to positive 9 newtons. Oh my god, that's the same exact answer, is it not? Look at that. Positive 9 newtons right here, positive 9 newtons right there, positive 9 newtons right there. It's all the same. So if at any point in time you want to go the other way, maybe you want to go from the right instead of the left, maybe you want to go from the bottom instead of the top, or vice versa, on any of those directions, it's all going to get you the same answer because we are assuming the correct direction for the force. Now, if you do assume the correct direction, the positive direction for our internal forces, this makes it easy to always see you get a positive number, directly correlates to the positive on the graph. But when in doubt, check it out for yourself. Do ask yourself, am I going away from the face, which is in tension, or towards the face, which is in compression? That's all you gotta do. So again, it doesn't matter how goofy it looks, doesn't matter that it's offset. You summon the forces either in the y direction because your thing's vertical or in the x direction because your thing's horizontal. It's all the same. They're actually pretty simple. And that's a wrap for axial force diagram.